Good afternoon, everyone, and welcome to this IMOS webinar. My name is Caterina Giusti. I'm professor of statistics at the University of Pisa in Italy, where this session is hosted. And today I will also act as the webinar facilitator. Now, let me first explain for any newcomers that IMOS stands for the European Master in Official Statistics, a joint project of universities and data producers in the EU member states, EFTA, and EU candidate countries. If your university is interested in applying for the IMOS label, please consider that a permanently open call for universities is available on the IMOS dedicated page on the Eurostat website. For staying in contact with the IMOS news and community, please follow the IMOS Twitter. The IMOS account is @EU_IMOS. It's now time to start with our webinar. Before I give the floor to our speaker, let me first briefly explain how we run the webinar today. As for the previous webinars, this year you know that the IMOS webinar stream on the IMOS YouTube channel, where you can already find the recording of all the previous webinars. As a participant, you can watch and listen to the webinar. To use the chat to interact with the presenter, you need to log in YouTube using a Google account. We encourage you to prepare your questions and put them to the presenter during the presentation or the final discussion. Should you have any technical problem or question, please use the email address that it is already indicated in the chat. So today I have the great pleasure to host Massimo Ciccotti, Professor of Molecular Epidemiology at the University of Biomedical Campus in Rome. And today Massimo will present about statistics and epidemiology, two inseparable friends. So Massimo, I leave the floor to you for your presentation, your slides. Thank you.
Oh, thank you, Caterina, to invite me. And okay, I can share my desktop. I don't know. You see my slide?
Yeah.
No? Okay, right.
Yeah. Now, yes, you are.
Yeah. Now.
Yeah. Okay.
Okay. Sorry. This is the last.
You are not at the top. Yeah.
No. To begin by the last. No, this is not usual.
Go to the first.
We have to begin by the beginning.
Yeah. Thank you.
So, thanks to invite me. I hope not boring you with this presentation, because I know that in the afternoon to speak about statistics or epidemiology there is a possibility to boring you, but I try to have the presentation light but strong in a concept. Statistics and epidemiology, two inseparable friends, because are inseparable friends. Epidemiology and statistics are connected, as you can see by the picture here, and are connected because epidemiology is a description of the studies, a description of something that can help you to understand a condition of the disease, a condition of a sort of epidemics, and so on. But statistics give the number, give the results of this study, and are very, very connection. There is a very great connection between them. Are inseparable. Do not talk about epidemiology if you don't have a statistic that support your design. You don't have and don't speak about statistics is at the beginning don't have a right epidemiological design. So and you can see when we talk, we will talk about molecular epidemiology will be the same. Is a branch of epidemiology, or was a branch of epidemiology, but now is a discipline apart. And you will see that the statistics is fundamental for also molecular epidemiology. Word epidemiology comes from the Greek words, meaning something a lot of definitions are for epidemiology, WHO definition, ACDC definition, CDC definition, but probably the right is the study of the distribution and the determinant of health-related states, or even in a specified population, and the application of this study to the control of public health, of health problems. The study of the distribution of determinant of health by the important point of view. Important point of view mean times, place. So the question is when something happens, why happens, and where happens. Statistics is a branch of applied mathematics, involved with the collation, description, analysis, inference, conclusion, are all is on quantitative data. All the mathematical theories are behind statistics. Theories like integral calculus, linear algebra, the theory of the probability. This is important. We can talk about, when we talk about molecular epidemiology, the theory of probability is very, very, very important to describe a phylogenetic tree, for example. Statistician is a people that normally study statistics and are concerned when determinants how to draw a reliable conclusion, normally about a large group. And we have two different theory of statistics, frequentist and Bayesian statistics. The frequentists need a large group of data. Bayesian statistics don't need a large group of data because it's founded on the probability theory, on the theory of probability. I have an opinion. If, for example, if I am a clinician, I have an idea about this disease, and I give you and tell you, right, your disease is probably due at. But I don't know. I don't know if my supposition is good, is real, is the solution of your problem. Probably is the solution, but I need to test by statistical diagnosis, a statistical test that give me the possibility to have a more robust, more the probability that grow up by the first hypothesis that I have done. The hypothesis is that the transaminases are high because you probably have hepatitis A. I have to test if you have hepatitis A. So my a priori probability can be assured by the posterior probability doing the test that give me the possibility to amount the probability. This is more or less, the Bayesian theory by the clinicians, by the aspect of medicine when I have an hypothesis about the cause of the disease. And statistician, when have a small sample size, is a portion of a larger group of person, sometimes is not so happy to have this kind of data. The happiness is have the large data as possible. But if you shift in epidemiology, epidemiology is a discipline where there is a sort of methods that give us the possibility to understand the phenomenon. Basic epidemiology is observational epidemiology, or better, epidemiology begin on observation. Observation and normally there is a comparison between different groups to assess, to evaluate whether there is a difference between these two groups. Difference probably due to the number of cases of disease in a particular area, in a particular time period, with a particular frequencies of exposure, for example. And if all these can differ from what I expect. I observe a phenomenon that normally I don't see during the observation period. For example, epidemic. Epidemic is the number of people that are infected by certain disease, and this number of people normally I expect that are 2-3 per day. When I observe 20 times per day, probably I have a problem, because it's not expected to have this great number of people infected by certain disease, hepatitis, HIV, what you want. And so this is the work of epidemiologists, or better, the observational epidemiology is the basic of epidemiology. However, also there are methods from other scientific fields. And because epidemiology need to have the help of biostatistics, bioinformatics, and also biologic. If you think, for example, all the microbiologists, virologists, bacteriologists that are involved in this pandemic that we are suffered by 2 years, and helped epidemiologists and statisticians with a great work, giving information about which kind of in this pandemic, this kind of viruses, what is the behavioral of this virus, and so on. But not only. Epidemiology means also economic and behavioral science. Observational epidemiology. If you think, for example, ecological studies, no? Ecological studies is the first studies that you can do when you face something, for example, tumor and air pollution, for example, in a certain area. You can do, probably you cannot do a sort of inference, but you can describe that you have a certain number of tumor and an A grade of air pollution in the same area. Probably this high grade of air pollution is the cause of the number of tumor that I have seen. Probably is an ecological study. Is not a study where I can do an inference. Talking about this A is probably A can support B. No, I cannot say that, but probably I cannot say that I have a low and high quantity of A, probably, and also I have a high quantity of B, probably A is due to B, or vice versa. But normally, epidemiology is used to describe the problems of public health. It is the basic science of public health. It is also not only descriptive in terms of observational epidemiology, but also is a quantitative discipline, rely the working knowledge of probability, statistics, and epidemiology is also a method of causal reasoning based on developing and testing hypotheses. Probably can group a lot of different fields as behavioral science, physics, health-related behavioral, and also is not only a sort of research activity, but is within a public health. Because public health normally includes epidemiology. Without epidemiology, I think that doesn't exist public health. Public health, I normally can be intended, that is the study of the health of a population in terms of disease. But without epidemiology, it is impossible to understand. It's impossible to have a picture of the situation. Within the epidemiology, within the public health, there is a statistic, because the statistic gives me the possibility to have a connection, a right connection between the phenomenon that I am observing and the number of disease, the number of cases of disease. But this is due to the random chance, is only a chance, a random chance, or is true that I am observing these cases of a disease in a certain period of time in this place, or is it true? Is a real problem? Statistics give the possibility to have the solution of this problem by the statistical, a huge number of statistical tests, a huge number of description in the statistical of the statistical number. If you have observed, I don't know in which city or place you are living, but in these 2 years, television, I don't give you the name because it's not how to say, is not correct to give a name, but this television every day give a so-called the number of pandemic. Number of pandemics was a statistical manner to give information, right, of course, to the people about the status of the pandemic, daily, weekly. It was at the beginning of the pandemic, it was important to give an idea to the people of the pandemic about how big is the problem. Epidemiology can give information about what I have to study, what I have to, which kind of variable I have to study, I have to give you. But the number give us the statistic. The statistic give us the reality of the situation, giving the percentage of prevalence, giving the incidence on a number of cases for 100,000 of inhabitants. Statistics and epidemiology, inseparable friends. Also in this case, epidemiology is concerned when the frequencies and the pattern of events in a public health, in a population, frequencies is not only the number of the health event, the number of cases, but also the relationship of the number of cases and respect to the size of the population. The rate, the resulting rates, give the possibility to epidemiologists to compare the disease occurrence, for example, across different population, across different places, in a different time also. Pattern refer the occurrence of health-related events by time, place, and person. By times, as I told you about the number of the number of pandemics in our case. Time patterns can be annual, weekly, daily, hour by hour, only the weekend. It depends by the time and the period of time that you want to observe the phenomenon. Place, obviously, is the geographic location, and urban, rural. And you can also, sorry, but sometimes I have to drink because mask can give us a problem in the throat, Place include geographic variation, urban or rural, location like, for example, workplace, different workplace, school, university, and to compare people that goes to the university, that goes to the place, different to the university. These patterns, place and place patterns include all these things. And then last is the more personal characteristics, the normal demographic factor, so normally is called epidemiological factors, epidemiological data, age, sex, marital status, socioeconomic status, and environmental exposure, and so on. All these characteristics are included in a study of public health. Time, place, person are activities of descriptive epidemiology. But more important, by my point of view, more important is to search the determinant of disease, the risk factor of disease. What is the cause of the disease? This is important because you can act to cure the disease only if you know what are the determinants, the risk factor. Because if I can eliminate the risk factor, probably I can eliminate the disease. Epidemiology normally assume that illness doesn't randomly in a population, but only when you have a specific risk factor or specific determinant in an individual or in behavioral of individual or in a place, in a place where these individuals normally lived. Is a sort of not only one specific risk factor, but also an accumulation of different risk factors altogether can give you the specific disease. The nature of the research of this determinant, how to say, are focused to provide the why and the how of such events normally happens. Different group with different rate of disease, why they differ, or I have to understand, or I want to understand, why they differ, why the disease is different in this group. Is different because there are demographic characteristics that are different because there are differences in genetic or immunological makeup, are different because it's different the behavioral, or are different because no one think by this point of view, are different because the virus, for example, is different because the viruses mutate. We have an example in this pandemic of the huge number of variants that we have seen. The virus was different, and the difference was in and not only the contagiousness of the disease, but also how was important the disease in terms of the gravity of disease. The group are a different rate of disease, different in all these characteristics. Determinant is a risk factor. Normally, the definition is any factor with an event, characteristic, or other definable entity, and so on, as you can see in a slide. But the real and the very, very short words are determinant are a risk factor for the disease. Epidemiology was focused normally in a communicable disease. Was focused in communicable disease because was important the role of communicable disease in the evolution of a human population. If you think to malaria, if you are thinking to cholera or other kind of diseases. And so originally was focused on only in a communicable disease, but rather than was expanded in endemic communicable disease and also in chronic disease, non-communicable infection disease. By the middle of the 20th century, so you can see the method had been developed and applied also in a chronic disease, injuries, birth, defect, occupational health, environmental health. And so the epidemiologists began to look at the behavioral related disease, tumor, and environment, for example. Now, with the recent explosion of molecular methods, epidemiologists goes through another way. Another way was important because begin to examine the genetic marker of the disease. The genetic markers as a risk of disease. And was important because change for example, the point of view of an epidemic. Normally, we can see the epidemic and we can say something about the epidemic when we observe a number of cases that are very, very high in respect to the number of cases that you are expected. This is our point of view. But we don't know the bacteria or the viruses how many times before that I have seen the cases, because the cases came after the infection. For example, you know that 1 week is the period of incubation at the beginning of this pandemic for coronavirus. Now it's 3 days with Omicron, but at the beginning it was 7 days. So I can observed the number of cases 7 days after the contact with the virus. How many days before the viruses are in my house before that I discover? Only reasoning in this kind of epidemiology that normally examine the genetic marker of the disease, only in this case I can discover how many times before. This is a molecular epidemiology, is a molecular evolution. And only in this case we can change my point of view. And only in this case I can anticipate an epidemic and not post-anticipate the point of view of epidemiologists about the study of an epidemic. Many epidemiology normally use the disease as a shorthand for the wide range, you can see, of health-related studies or event. Disease is indifferent which kind of disease. I find that is not completely right. I not completely agree with this term, because there are disease and disease. Is inopportune to define disease in general. Also to discriminate between communicable and non-communicable disease. But within these two great differences, communicable and non-communicable disease and infection disease, for example, I don't find that it's very correct to define disease in general. But each disease is behavioral, have a curve that can represent the disease. And the diseases are different between them. For example, an RNA virus, you have an evolutionary rate of more or less 10 and -3 level. And hepatitis B, this DNA virus, is not so high rate of evolutionary rate, but is 10 elevated than -5. Don't run as an RNA virus. This is important to distinguish between them. After that, we have to give something news about specified population. Maybe Caterina, sorry if you are in line. Maybe,
yeah, sure. I'm here. Yes.
Sorry, no, because I don't
Time
know.
is running, of course. Yes, you can go if you
I
want
have to run.
Yes.
Yes. I can imagine. Okay, right. You can see specified population. Epidemiology is another study of health in a population. There are all these sentences.
Massimo, sorry. Yeah, just to specify that, of course, your slides are available. If people, I mean, they can read them later, of course. If you want to skip something and go to the next part.
Yes, because I exactly. Okay, Caterina, I can run die regression, the use of statistics. All right, epidemiological study. Everybody knows. I want only to describe, really in three words, the study design. This slide can resume all the type of the study in epidemiology, descriptive and analytic and observational studies. You can begin by observational study, prevalence study, normally, or ecological study, or case report or case series studies, of course. But then you need a type of study that imply the analysis, they imply the statistical analysis within this study, cross-sectional studies and longitudinal study. It's very easy to describe this study, hypothesis testing, right? But for example, okay, test the T, test, no, I want to go to the study. Here is a case control study. Case control studies is important. Case control study give you the idea of the probability that risk factor, a certain risk factor, give the disease. It's very easy as a study. Very easy, and is important the statistic within this kind of study, because it is behind the time, is run back in the time, and the beginning is the number of cases that you are observed months ago, and you have registered in a database, and you have to observe, to compute how is the exposition that give you the cases. What is the statistic within this case control study? It's important to give you the validity, the statistical significance of the odds ratio, the rate of odds. Also, the probability that the phenomenon can happen over on the probability that the phenomenon doesn't happen. The odds ratio is the rate of these two probability. There is a confidence interval that give you the possibility to have a statistical that can support, and they give you the validity, the statistical validity of the study is, supported by the statistics. Is statistical significant or not? It depends by the confidence interval. Where is not supported by the statistic? When the confidence interval contain 1, the number 1. Why? Because if I have 1 in this interval, the numerator is the same of the denominator, and the probability that something happens is the same that the probability doesn't happen. So if I have the unit 1 in this confidence interval, there isn't a statistical significance. Or if it doesn't contain the unit, is a statistical significant. Okay, this is the statistic in a case control study, but also in the longitudinal studies, when I have the relative risk and known the odds, because now I have the incidence in terms of epidemiology, because I'm going over on the time. I don't back on the time. And going over in the time, I have exactly the time when the person was infected. Having the time when the person was infected, I can compute the incidence. If I have the incidence represents the risk of disease, the real risk of disease. When I have the incidence, I can to have a rate, or better, the relative risk, how these incidents, how the risk is so power that I'm sure that this is the very risk factor for the disease. The same, the confidence interval doesn't contain the number 1, because numerator and denominator are the same, so I don't have any difference between case and control, between person with the disease, person without the disease, when are in the presence of the risk factor. So in this case, how you can see 6.67 means that I have the risk of a disease that C times more that do not have the risk of disease in the presence of the food poisoning. Experimental study, randomized control trial. Also here the statistical is important. The intention to treat. Intention to treat. When you have the lost in a follow-up that are more than 20% of the people that are involved in a trial, you can use the intention to treat statistical system, and so you can do not have a bias in a study because you don't have a 20% of people that you have lost during the follow-up. And the sample size that you have computed at the beginning of the study can remain more or less the same. This is an important statistical support for a clinical trial, but in general for longitudinal trials that have a follow-up. The loss to the people lost at the follow-up. Then intention to treat concept, and now, so we can go toward the end of this presentation. The difference between classical epidemiology and the molecular epidemiology, the new epidemiology, the human point of view in terms of cross-sectional study, case control study, and cohort studies, but the same by the microorganism point of view, phylogenetic analysis, evolutionary analysis, and phylogenomics. This is a first step, important, where statistics is necessary, and the particular statistics are two particular statistical concepts that we can apply in a phylogenetic analysis: maximum likelihood statistics and Bayesian statistics. And maximum likelihood is within the creation of the data set, the sequence alignment, because we are working about the genetic sequences of a certain protein of the whole genome, if it's a very short genome, like also coronavirus is possible because it's not so big, HIV, for example, or other RNA virus, but hepatitis B is not possible, or microorganisms like bacteria is not possible. We can work on a specific protein, not a great number of nucleotide in a sequences. But normally, the first step is the creation of data set. Statistics is within the creation of the data set, because we have to choose the most similar sequences in a database. There is a score, of course, mathematical score will give the possibility that the sequences are more similar to the other sequences with respect to other one. And so we can create this database. Then we can align the sequences. Also, the statistic is within the sequence alignment, because it's a mathematical model that gives us a score, a specific score, and depending by the score, we can align. And if you have a good alignment, probably, no, I'm sure, not probably, I'm sure that the phylogenetic tree that we normally build after the sequence alignment give a real picture of the situation. Then we can study the evolutionary mathematical model to give not only phylogenetic tree, but to evaluate the evolution of your sequences, how they move over time. And the study concerned to reconstruct the evolutionary history of the species, of the genes, of the genome, are all, as you can see, the algorithm approach, and come from genetic data, but molecular phylogenies is a very, 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 very great impact in infection disease, especially when we have rapidly evolving infection agents, such as RNA viruses. And this is very important. Why is important? Not only the epidemiological surveillance in a case of this pandemic, because it's an RNA virus, but it's important and molecular epidemiological surveillance, because we have to act directly on a genome, not on a person that was infected, but by the virus point of view. I go on. So this is an example of a phylogenetic tree. This was our first paper that we published in January 25. So January 25, in January, the year was 2020, was at the beginning of epidemic. The WHO claimed that the December 2019, 31 December, at the end of the year, that was important. That was an important epidemic in China, in Wuhan. After that, we immediately published this phylogenetic tree, and so if you can see the branch of the tree, if you explode this triangle, you have these sequences. The sequences that was isolated by the first people infected by the virus in China, and we discover the spillover from the bat to man, and we have the possibility to date exactly the spillover. The spillover we computed that was at the more or less 25 November, in 2019, with the confidence interval that went to the end of September to the end of December. So the spillover was in a time of what we have seen. This was important, and the number that you are observing here, 1.0, 0.9, and so on, are the statistical significance of a clade, because behind this tree, there is a statistic that gives the opportunity to have an idea that this tree is a very real tree, because we can build a tree, but is the true tree that can explain me what I have seen by the epidemiological point of view? I don't know. I need the statistical support. This maximum likelihood statistical support gives us the possibility to say that this cluster at 100% is true. This truth means that all the sequences, all the viruses isolated in this context are identical, are the same virus, represent the same virus, non-different virus. Each clade is formed by the same kind of viruses. And this is true at 90%, 90%, 1%. Not only we accept by 90, 92% more, not less than, absolutely not. If you can see, the terminate node on the cluster here are not significant, but significant are this one, and this big cluster, 100%. This means that all the sequences come from the same population, come the same population of viruses, and probably it's the same viruses. Also, we can, these are the two words, we demonstrate that in Italy there was two different epidemic entrance of the viruses. In the north of Italy came from Germany, and in the center of Italy came from North Europe, more or less UK, more say probably UK. And these other three represent the couple of Chinese husband and wife that came in Italy and was found infected by the coronaviruses. And dating, you can see by the Bayesian method, statistical Bayesian method, dating the evolution of the virus that infected these two individuals, we discovered the time of incubation period. They was infected before arriving in Italy, was infected in China. At the time of the symptoms was 10 days, 1 week. 1 week was exactly the incubation period for the viruses. We are talking about the strain of one, the old strain of one that doesn't exist now. And so on. This is the epidemic that we have in Italy, and the same phylogenetic tree and the statistics with the frequencies explained in frequencies of different mutation. And then, this was the origin of Zika virus. We studied in the northeast of Brazil. Zika was a problem at the time. And now, so we are in a time, 1 minute, I'm in a time, I'm happy. This is the other, the other phase of the epidemic or pandemic, the cost. The business closed to 255 million full-time jobs lost. The consequence of the epidemic, the consequence of the pandemic, in terms of working out hours in 2020. You can see here the impact in the society, the education. You can see how many students was out of school. The investment in clean energy transition, minus 30%. People pushed into poverty in 2030, 251 million will be in 2030, and the cause for is this pandemic. And now, extremely poverty. You can see in 2018, 2019, look at 2020. Grow in a 7.1%. We have spent a surging $16 trillion providing physical support and the deficit. Wealthy country that have, this is a report by Oxfam, the government is sure to support people through the pandemic in 126 low and middle income countries per person in low and middle income country by $4 to 28. Person in a wealthy country, say $695. So I'm in time, maybe Christina, only 1 minute more, 2 minutes more.
Yes.
Sorry, but this is a very risk, the real risk of a pandemic. If you study the story of infection disease and the history of the pandemics that we have had in the time when the human lived, the cost of the pandemics was in people died, in poverty, in the environment, And in poverty means that a lot of people goes in a poverty because closed the stores, didn't have a job, and a sort of accidental. That pandemics is not only disease. Pandemics is not only disease, but is also this kind of situation, you can see now. Thanks.
Thank you, Massimo. Just two quick questions that I received by email. So one question is about the pandemic. I mean, did you use new methodologies in a sense with this pandemic? It was a challenge and you developed something new? Also this paper that you were addressed to, or did you learn something new? That was the question, very general question from this pandemic, also from a methodological point of view.
What changed, for example? We in Italy we didn't believe the difficulty of this pandemic to face this pandemic by new kind of instruments like molecular epidemiology, for example. If you think that UK create a consortium in March 2020 to discover the variant of the virus. But why you want to discover the variant of the virus? Because the vaccine have to cover the variants. Vaccine that I'm studying can cover the variants. This was the question. Which kind of viruses are in my countries, are circulating in my countries, or in European countries different from my country? I have to find some. At the end, we put in a field all the specialized how to say harms that we had. For example, people at the beginning was the care of the people was tachypyrine, was oxygen, was cortisone, was a lot of drugs, antivirals, but not enough. For example, monoclonal was not approved. Was how to say? There was a bureaucracy that stopped a lot of important drugs, a lot of important also vaccines. You can imagine how many vaccines was stopped in phase 2, in a trial in phase 2, because don't supported by the government, or not supported by the law of the government, not supported by a blah blah blah, or because are not created by the multinational pharmacy. The case of AstraZeneca, the case of Johnson & Johnson, the case of Sputnik 5, the case of Sinovac. Why? We used only Pfizer and Moderna vaccine. This was the real problem of this pandemic.
And a very last question, also not related to the pandemic, but in general, do you have also some, if you want, I mean, to compare the prevalence of the same illness at European level? Is that possible? Do you have some data set or not? Just local data each? Okay.
No. Yes, you're right. This is a very good question. The example was the prevalence of death in different European countries. For example, if you look at the curve of the death in a month, in the last month, daily death per day, the curve of Italy is more or less high. The curve of England is less, is under the curve of Italy in number of deaths. Why? They do not have a mask. They don't use any kind of support. They are free to live as they want. Vaccination? No, because more or less are the same percentage. The definition of death. If you don't have the same definition, you don't have the possibility to compare. This was the problem. The problem was easy, Cristina. If you look to Italy, the different region of Italy give you the different number, the different prevalence of something that you want to look, because are different. The mood, the modality of to describe the data, the definition. What is the case definition? What is the mortal definition? The death definition are different with COVID or for COVID. If you don't have an homogenization of this definition, you can't compare. You can't compare anything. The comparison is not possible. I don't know if England is the best of Italy or the contrary, or Italy is best of Netherlands or Germany or French. I don't know.
So maybe here, an harmonization would be nice to try to have at least.
Yes.
Exactly.
And the error was done first by the WHO. Don't give the same definition. Don't say it. All the nation must have the same definition of death, the same definition for cases, the same definition of WHO didn't give any news about. But also the ECDC. But ECDC is only European CDC. WHO is all over the world.
Worldwide,
It's worldwide. You can give me the definition. Don't give me the possibility to have the Greek
interpret.
But no, you give me the Greek alphabet to describe the variant, but it's not interesting. Variant from India, variant from England, this is the same, not alpha, beta. But what mean that? Give me the definition of case, the definition of death.
Okay, thank you, Massimo. I think we have to close. So thank you very much for your interesting presentation. Many thanks also to our participants. So the presentation is already available on the IMOS 2020 events website, while the recording of the webinar will be available on this YouTube channel. And you will shortly receive, or I think you have already received, the email address that you used for registering to the webinar, the link to a short survey about today's webinar, and really appreciate your feedback to further improve our webinars. So the next IMOS webinar is scheduled on Wednesday, March the 2nd, when Joe Roisling from the Norwegian University of Science and Technology will be presenting on statistics more than number. So thank you again, Massimo. Thank you to everybody, and have a nice evening. Bye-bye.
Thank you, Cristina. Thank you, everybody. Bye.
Bye-bye.